In this video for VCE algorithmic students, I'm going to explain the basics of neural networks by using a simple neural network which is designed to learn the difference between cats, foxes and dogs. It uses just two inputs, which is unusually low, but it makes the visualization easier. I'll also be a bit casual with some of the maths, but you're not required to get into the real tricky details for algo anyway. As you can see, the input layer is made up of two input neurons, which are corresponding to size and ear pointiness. Every piece of data is evaluated on these two criteria and given a value between 0 and 1. Next, we have a hidden layer containing three hidden neurons. Again, in reality, there are many layers of many neurons, and we don't actually know what they all do, part of the mystery of neural networks. Each input neuron is connected to each hidden neuron by an edge with a weight. Here you can see one example. The weight is initially random and small. Each neuron is going to have multiple edges, and each time we iterate through for the top neuron, you can see there in this example, we're going to multiply each input by each weight, add them up, and then also add a bias. The bias in this case starts at 0 and is set for each of the neurons. This calculation gives us an output, in this case 0.18. This output is in turn put into an activation function. There are various functions, and again you don't need to know the maths behind them, but here are two examples. We have a step function which outputs 0 or 1 based on the value of x. You've seen plenty of these in maths methods. We have another function here, and if we put x into this one, we get an output of 0.5449. Okay, depends on how you set your network up as to what these values will be. The output of each neuron is the output from the activation function. So just to repeat, for each neuron in the hidden layer, we take all of the inputs, multiply each of them by the corresponding weight, and then add a bias to give us an output, and then put that into an activation function to give us the output from the neuron. And then this will go through many other layers of many other neurons. So we can imagine all of the network is built up using lots and lots of edges, as you can see. The hidden neurons map to the output neurons in the same way. The three output neurons give us a probability that the input we have provided is either a cat or dog or a fox. Note that this is different to, let's say, a support vector machine, which will just give us a binary classification, yes or no. Next, we train our network with some known data. Weights are shown on the edges, biases in the nodes. The values themselves don't matter here, just be aware that they are initialized randomly and low and that they exist. We input the values for a fox and we receive some output corresponding to the probability that this animal is a dog, a cat or a fox. Ignore the fact they don't add up to 1. Now we should have probabilities 0, 0 and 1 because we know this is a fox, it's not a cat or a dog. So we're going to find the mean of the sum of the squares of the errors, a little bit like when you find standard deviation, as a measure of accuracy of our neural network. Square them, add them, divide by the number of neurons, and we get some value. Now we need to train our neural network using backpropagation. The process and the maths behind this is not required for VCE algorithmics, so you can ascribe it to the mystery of faith, but if you're interested, once we know the output for each neuron and we know the corresponding error, we work backwards from the output to the input to work out how much each weight and bias contributed to that error. This gives us a gradient for each of those parameters, so the weights and bias are parameters. And then we nudge every weight and every bias a small amount in the direction of those gradients. We don't necessarily do this one image at a time. We might go through a batch of images at once, but we do go through the training data many times, and each of those passes is called an epoch. So we've done this a whole bunch of time using our training data. We are now ready to see how well our neural network can do its job. Next, we enter the validation phase. We take data that the model has not seen before. We put it in and we do just the forward propagation phase to tell us an overall error. This is important because if we only ever use training data for our validation, there is a risk that the model will overfit the data, which is where it only really learns the specific examples without having boundaries that can be relied upon for all examples of future cats, dogs, and foxes. This is why we must never modify the parameters of the model based on the validation set, and we must never let the unseen validation influence the training phase in any way. It's called cross-contamination. Now, these visualizations give you an idea of how this looks. Here we have some well-fit boundaries. We can see the cats, foxes, and dogs in those colors, and we can sort of see where those boundaries exist. They're not hard lines. This is not exactly how it works, just so you can picture the situation. If we overfit, we end up with boundaries that fit the training data really well, but they don't capture the overall pattern of what's going on. So you can imagine, especially down near the green and the orange where they get very close together, you can imagine this model misclassifying a fox as a dog or vice versa, because it's overlearned the specifics of the training data without really, I say, understanding foxes and dogs, etc. It's a bit risky to say understanding, but hopefully you can see what I mean. When we're talking about errors with neural networking, if we're talking about overfitting, we should also discuss underfitting. And what you see here is an underfit decision boundary where we don't run the training enough times, we don't do enough modifications, and we end up with boundaries that don't even fit the known data particularly well. There you have it. That's a very quick summary of everything you hopefully need to know for neural networks for VCE algorithmics. You can also have a look at the Python code. Hopefully I've managed to attach it to the comments.